Okay. Okay. So good morning, everyone. Thanks for staying until the end of this conference. I personally enjoyed it a lot. Had a little bit too much food and too little sleep, but that was really great. So I would like to tell you today about recent works that we've done in the field of quantum simulations using quantum computers on the cloud. And I would like to start by acknowledging the excellent work of my research team. Some of the students are here. You have met them. Some others already graduated. So we were lucky to work with very advanced research partners, IBM, Microsoft, and Amazon. And in particular, I would like to acknowledge Rigetti, with whom I spent a sabbatical year this year. And the funding is from the ISF. Okay. So quantum computing on the cloud has been mentioned before, but let's just for the students, try to map what is the current status of the art. And when we think about quantum computing on the cloud, what one should have in mind is basically currently IBM, Amazon, and Microsoft are the main leaders in the field. And what they allow you is to connect to real hardware. So in the case of IBM, you connect really to the IBM quantum computers. Amazon and Microsoft don't have yet their quantum computer, but they allow you to connect to quantum computers provided by other companies. And they belong both to superconducting circuits, like in the case of D-Wave, Rigetti, and Oxford Quantum Computing, or ions, as in the case of IonQ and Honeywell, now known as Quantinuum. Let me give you an example. So probably most of you have already seen the example, but there are a few points that I would like to highlight. So let's consider, for example, the IBM case, and assume that you want to create this GHZ state, so 0, 0, 0 plus 1, 1, 1. As you all know, this is the circuit that creates that state, so it's one atom to control node. You realize it, in theory on the simulator, the measurement should give you 50% 0, 0, 0 and 50% 1, 1, 1. And, but when you run it on the quantum computer, if, for example, in the case of the quantum computer IBM Q Lima, you get results that look like this. So you see that there are, first of all, some strong asymmetry between 0 and 1, and also all these results that should be 0 are actually non-zero. And these results were taken a year ago. So just before the talk, a couple of days ago, when preparing the talk, I rerun the algorithm. Instead of Lima, I ran it on Jakarta, and these were the results. So apparently, it doesn't get much better. Although you do see that these numbers are a little bit smaller. So the asymmetry is bigger, but these numbers are smaller. The asymmetries can be fixed by error mitigation. So maybe overall, this is a little bit of an improvement. Okay, good. So this is the world where we live for a very small circuit of three qubits. And so this leads me to speak about noise and errors. How can we estimate how good the quantum computer is? So I would like to provide a very simple thumb rule for a guidance, like a practitioner's guidance of what can I do with a given quantum computer. So for instance, let's take the case of IBM Quantum Jakarta. There are many numbers, but let's focus on the numbers that are most relevant here, which is the CNOT error and the readout error. So the CNOT error is about 1%, and the readout error is about 3%. And these are the same numbers that were presented yesterday by John Martinez. So these are pretty good numbers. What does that mean in practice? How many qubits can I use? How many gates can I use? So I would like to present my own thumb rule. Already John Martinez spoke about it, the idea of multiplying probabilities. I'm not very good in multiplication, so I'm proposing a sum. So you basically just take, this 1%, 3%, sum how many gates you have. If you have 20 gates, then it's 20% plus how many qubits you have. This gives you a rough estimate of how error you have. When it is below 50%, don't even try it. So this is roughly and it works. I mean, you can get a rough estimate of what can be done. So in particular, people look at a square circuit. So a square circuit is a circuit in which a number of qubits and the depth is the same. I mean, this is not, but it's just common for convenience to consider that case. And then you may ask, what is the largest square circuit that I can realize? So in this case, you can realize 5 qubits times 5 gates, you know, it will give you approximately about 50%. If you put 6 qubits and 6 gates, you go above 50%. And that means that the quantum volume, so the quantum volume is 2 to the power that size of the square circuit. So in our case, we have 5 qubits, 5 gates, so the quantum volume is 2 to the power 5, which turns out to be 32. So this is, you know, my own analysis, and it can be confirmed by much more advanced analysis of quantum values, randomized benchmarking, etc. And you will see that these are the typical numbers for an IBM quantum computer. So overall, this means that in superconducting circuits, you can use at most 5 qubits. Okay? So the goal of my talk today is to try to convince you that you can do something with these 5 qubits, and it's interesting. Okay? So I will give you actually 3 different examples of recent projects. Some of them, one is published, one is in the archive, and one is to be submitted soon. So the first project I would like to tell you about is how to simulate a Bose-Einstein condensate with just 5 qubits. So what is a Bose-Einstein condensate? I see there are many students in the audience. So what is a Bose-Einstein condensate? Yeah, but what is the definition? I mean, you know the answer, right? It's not a secret. So, okay, I'll say the answer. You see, you are shy, but you all know the answer. And the answer is that this is a state that has a macroscopic occupation of a ground state. So there are many, many atoms that all sit in the same ground state. It happens for bosons. I'm sure you have all seen this picture. What this picture is telling you is, well, this is not a Bose-Einstein condensate, this is a Bose-Einstein condensate. So here there are a few particles in the ground state, here there are many particles in the ground state. Okay, this is as deep as I want to go right now. But there is another definition which is basically equivalent, and now Alessandro, where is Alessandro? I challenge you to do this with your iPad. The other example is that you can define the Bose-Einstein condensate in terms of a coherence. And the way to probe the coherence in PowerPoint is, and you cannot do it in an iPad, is this way. So you take the two condensate and you let them expand, okay, until they overlap, and then you measure just the number of atoms. It's a very simple example. I mean, philosophically simple experiment. You take the two Bose-Einstein condensate, they are in a trap, you release the trap, they expand, and then you count how many particles they have. And what you will see is an interference fringes, okay? So it means that there is a phase coherence. This is, now you can start, Jörg has studied, much more detail. This was 1D, not 3D. I mean, there is a lot of physics in there, but the main, the main experiment is just an interference experiment. So in this talk, we have spoken a lot about philosophy. For some reasons, Greek philosophy is very common. So I would like you, because we are here in Israel, not far from the Galilee, I would like to present the Jewish philosophy. And the Jewish philosophy is mostly about language. Actually, two different people asked me, do you study Talmud? So these are the two opinions that we have, right? The typical situation of the starting point of the Talmud. You have two different opinions of how you define a Bose-Einstein condensate, and how do you solve the problem between these two opinions. How do you decide which one is right? You go, not in the Talmud. I mean, yeah. So how is it typical? I mean, there are two opinions in the Mishnah. What does the Gemara do usually? Yes, they ask another question. So you don't resolve the problems, just add more complications. And as we are luckily, after Kant revolution and Wittgenstein, we know that philosophy is mostly about language. So what I would like to propose, I think that the language of the Talmud can be useful here to study this problem. Okay, so what is the difference between a Bose-Einstein and a riser? And why the question is interesting? Because if you look at the two definitions that I gave you, you will say, well, these two definitions also apply to a laser, right? Certainly you have a macroscopic operation of a mode in a cavity, right? That's a laser, and you definitely have interference. So if you consider that, so then what is the difference between a Bose-Einstein condensate and the laser? This is certainly, you could think of it as the starting point of the Gemara, and then it boils down to, many, many different opinions that are given to find this solution. Maybe some rabbi will say, well, sure, there is no difference. I mean, a Bose-Einstein condensate and the laser is the same. Some others will speak about maybe the Boltzmann distribution of the non-condensed particles. I would like to tell you our own answer, or one possible answer. All answers are good, but one possible answer is that there is a difference in the terms of particle conservation. Why? Because in a BC of atoms, the number of atoms is conserved. I mean, if you take 10 to the 5, 100,050, well, whatever, 10 to the 5 atoms, and you to put in a trap, then the number is constant. I mean, they cannot escape. You cannot create atoms out of nothing. They could escape the trap, but this is a slow process. In contrast, in the case of photons, the number of photons is not conserved. The number of photons is not conserved, first of all, because they escape from the, if you want to have laser, you'd better have something that goes out from the laser, otherwise it's quite useless. And there is also a pump, so there is, all the time new photons enter and exit, etc. So the number, and there is no conservation law for the number of photons. Okay? Although they are both bosons, but they are bosons of a different kind. And you may think that, okay, who cares, right? Then this would be the Gemara question is, why would you care about this difference? What is the consequence for our everyday life? How this impact the way that we respect Shabbat in some way or another? And in our case, how it actually affects us a lot. And the reason it affects us a lot is that we know that the number and phase are canonically conjugate. So when I'm telling you that the number of particles in the BEC of atoms is conserved, it means that you cannot have a global phase. Because if your n is conserved, if n is fixed, phi cannot be fixed. It's a maximal uncertainty. So that means that in a laser, that's fine. The number of photons is not conserved and you have a phase. But what about the Bose-Einstein condensate? And here you get to sort of a, you may ask, okay, but in the previous slide, you tried to convince us that the Bose-Einstein condensate had a global phase, has a phase coherence, and now you're telling me that, I didn't show you experiment that there is a phase. And the answer to this paradox is that actually, if you repeat this experiment many times, what you will see is that every time that you perform the experiment, the phase is going to be different, okay? So in that sense, there is a phase, but the phase is undetermined. In every experiment, the phase is going to be a different phase, and really what the Bose-Einstein condensate has is the phase is a phase coherence in the condensate. So you have long-range correlations, you have an order parameter, long-range correlations within the Bose-Einstein condensate, but you do not have a global phase. So the global phase is unfixed. I'm going to come back to this point in a moment. While in the case of the laser, this is not the case. Right? In the case of the laser, if you do an interference experiment, then the interference is fixed. Right? So no global phase for Bose-Einstein condensates, and global phase in the case of a laser. Okay, so this is our own solution. And as you all know, the uncertainty relation is actually an inequality. Right? So it means that if you fix one, you cannot fix two, but you may also have a situation in which you fix neither. Right? That's also fine. You have large fluctuations in n and in phi, and in a sense, in our view, this is essentially what when people speak about Bose-Einstein condensates of light, these dye molecules, I don't have time to go into the details of the experiment, but those who have heard about the BC of light, which are BC of photons, and they are not lasers. One reason why they are not lasers, in our perspective, is that both the phase and the number are unconserved. So this is a very simple, idealized model of what is a Bose-Einstein condensate and what is a laser. So our goal is to simulate this difference in a quantum computer. So how do I create a Bose-Einstein condensate in a quantum computer? And the way I do it, I am going to do it in 5 steps. So step number 1, I prepare a laser state. And the laser state is a coherent state. And the coherent state of qubits is just very simply a polarized state of qubits. So what you do, you just take each qubit, you have in this case 4 or 5 qubits, and you prepare a superposition state. So this is a coherent state, and this is, it's the equivalent of the coherent state of a laser. Why? Because the direction of the qubit on the Bloch sphere in the XY plane is equivalent to the phase. Okay, so the phase of the laser is just the direction of the qubit in the Bloch sphere. And here I have, I have many qubits and I all prepare them with the same phase, so this is giving me a state that has some analogy to the laser. So that's step number one, and actually it's very easily achieved, just take your qubits and add them up. If you don't like the Hadamard, you can, this is selecting basically the zero phase, but you can choose whichever phase you want by just rotating in the XY plane. Okay, so so this is a laser. So here I created a state that looks like a laser. How do I create a state that looks like a BC? Remember, what is our definition of a BC is that the total number of particles is conserved. So what I need to do is to first measure the number of particles, and we do it with the head of an ancilla, and then post-select the correct number. So depending on the results of the ancilla, I will select the state of the ancilla that corresponds to a given number of total particles. Okay? So when I go through these three simple steps, I have created here in the output a Bose-Einstein condensate of qubits. So how can I convince you that this is the case? Well, I need to provide I need to do some sort of analysis of the state, of this output state, and convince you that indeed this is not a laser, this is a BEC state. So how do I do that? Well, as you know, in phases of matter, what you should look at is the order parameter. In our case, the order parameter is basically the total spin in the XY plane, right? So you measure the total spin in the XY plane, you repeat the experiment for all different angles, and then what you do, you can plot a two-dimensional plot like this. So the angle, the azimuthal angle, is going to be just the azimuthal angle in the XY plane, which is basically the phase of the laser. And the amplitude is going to tell me, this is the amplitude of the order parameter. Okay, so it is telling me that there is it is long-range coherence. So if there is no long-range coherence, then, most of the probability is going to be here, and having long-range order, it means that you are somewhere on the outer of this figure. So how is a laser? So a laser, as we discussed, is a state that has a well-defined phase. Okay, so this is a coherent phase. So you see, this is a state in which all the qubits, and basically this is a simulation in which I just prepared all my qubits in the zero angle. So that would be this is very simple to realize. What is less trivial to realize, and this is done by the circuit that I described before. So we measure the number of atoms and we post-select the correct number, is given by a state that looks like a BEC of particles. So this is a BEC of particles with 10 particles, and as you notice, what the main feature here is that, first of all, most of the probability is in the outer sphere, meaning that you have long-range phase coherence, that you have a well-defined order parameter, but the phase itself is undefined, right? So there is isotropy, the result is isotropic. So every time that you measure, you get a different phase, but all possible results are equally probable. While here, there is a given, a fixed phase that you must observe. And then there is also the BEC of light. I don't have time to discuss this. This is also interesting. It's also isotropic, but there are some interesting differences. You see there are some selection rule in the BEC of particles. You see that it's actually zero. All the odd rings are zero. That's related to the second order coherence of a BEC. But you can read it in the paper. Anyway, I promised an experiment. So let me show you how this is done on the Rigetti hardware. Can you turn off the recording for a moment? No, I'm just kidding. But the Rigetti hardware is very noisy, okay? I said that politely. Okay, so let me show you the results. I'm showing you the results of the theory and of the experiment. And I want to claim that this is interesting. And I think this is interesting for three main reasons. Reason number one, you see that there is no global phase coherence. You see that, there is no global phase. So there is some, I have instead of having 360 degrees, I have approximately 90 degrees. So there is some uncertainty, but it's not a complete uncertainty. Why is this the case? The reason is that I'm using only one ancilla. And in general, if you have n qubits, you would need log n ancillas. So here I would need two ancillaries. If I want to recover, this perfect 360 degrees isotropy, I would need two ancillaries. If I have only one ancilla, you're basically measuring the parity of the number of the total number. But I would like to use two ancillaries, but then I would need 6 qubits, and the quantum value kills me. So okay, so that's interesting. I mean, this is something that had not been studied before. It's a little bit like, what if I have a partial knowledge of the number of, I don't know exactly the number of particles I have, I say no, the parity of the number of atoms, how that affects the phase. So this is number one. Number two is, and we got to these questions because we have a limit number of ancillaries, because we have a noisy quantum computer. Point number two, there is a phase offset. So you see that the center here is in the top, in the bottom right, and here it's in the bottom left. And this is related to the fact that everything is rotating due to crosstalk. So if you want, this is also a way to measure the crosstalk between the qubits. And there is a topic they didn't touch upon, which actually when you really, there is a way to, just measure the order parameter itself, the long-range coherence, you will see that the BC state is actually more coherent than the laser state. So this is an interesting observation that we may, start playing around with those states. Okay, so, yes?
You have time to repeat just the definition of the phase and the particle number?
So the particle number is just the number of excitations. So 0 is 0, 1 is 1. So I count how many qubits I have in the one state. That's just the number of particles.
Some of sigma z.
Yes, sum of sigma z, yes. Sum of sigma z is just the number of particles. And the phase, it's always tricky to define the phase. So the right way to define the phase is to look at this order parameter, which is basically, the phase is just a direction in the xy plane. Okay, so that's just the phase that we have.
Of kind of a sum of the...
Yes, I take the total spin, and the total spin in each direction, and that gives me the phase. And then, okay. Yeah. So there is no phase operator. It's not easy to define a phase operator. What you do, you look at the order parameter, and that defines for you the phase. Okay. So the project number 2, it's called a non-local game. Here, I admit we use 6 qubits, but it's a very shallow circuit. So we can we had just a few gates, not too many gates. So what is a non-local quantum game? Is essentially like a Bell inequality with many qubits. For example, this has been proposed, I want to consider a specific non-local game, which is called the triangle game, and it was introduced by Bravi, Gosset, and Koning in Science, and then explained to us in this PRL, because with the science paper, it's whatever. So the game is built in, it was written, didn't mention, but this was a work done in collaboration with Daniel Atzitz, who is here. So the game is built in such a way that you can compare classical players with quantum players. The quantum players always win, and the classical players wins only 7/8 of the times. How does that game look like? So there are 3 players. It's a collaborative game. So they all try the game. They all try to win. And what does it mean to win? It means to satisfy some rules. So each player has 2 qubits, and they need to decide about the values of their qubits in a way that they satisfy some rules determined by the dealer. The problem is that the rules themselves are determined by some random numbers. These are just coins. And each player knows only the outcome of its own coin. So if they knew what were the results of all the coins, then it would be very easy because they knew what are the rules. They can just decide how to play. But the problem is that every time they play, the rules change. And it's a little bit like, a scientific publication, right? Every time it's a different reviewer, so you don't know what are the rules. And so maybe you know one of the reviewers, but you don't know the other 2 reviewers, so you don't know how to fix it. And of course, you're not allowed to transmit information between the qubits between the players, because they cannot talk to each other. Otherwise, it would be too easy. So here,
what do you mean by
rules? The rules? Yes. So these are the rules. So these are the rules that need to specify, and the rules depend on. So these are the variables. Each player has 2 variables. So x1, x2 is the first one. x3, x4 is the second. And depending on the result of the rules of the coins, you have different rules. So which means it's like playing 8 different games, and you don't know which game we are playing right now. So that's the problem. So the best classical strategy is actually they write 0 on all the qubits, and they will win 7, 8 out of the time, 7, 8 out. So they can win basically seven times except the first one. That's the way the game was built. How the quantum players are going to have some advantage, because before beginning, they are cheating a little bit. Before they start playing, they share among themselves a quantum resource, which is the cluster state. And then what they do, they perform a measurement on the cluster states, which depend on the result of their own coin. So depending on the result of the coin, they either measure X or Y. And as you know, because of the locality of quantum mechanics, when you perform a measurement, you're actually affecting you're somehow affecting the quantum state, and therefore you're affecting the outcome of the other players. So although you're not telling what is the result of the coin, you can somehow have these non-local correlations that will help you. And indeed, the game was built in such a way that the perfect quantum player will win with 100% of probability. Okay, the game itself is just based on basically a Mermin inequality. You can think of it as just as a Mermin inequality of the cluster state. Well, what we did, we just did some error mitigation. Notice that the error mitigation is done on each qubit independently, on each player independently, because you are not allowed to. Okay. So what are the results? As you can see at the beginning, we were not able to cross the results with the quantum computers that we have in hand. Then Honeywell came and said, oh, we actually have in our backyard a better quantum computer, and that was able to cross the threshold. So this quantum advantage here, or quantum violation, it's very much related to the numbers I told you before. You can see that the IBM quantum computers are close to this threshold. This was a very old quantum computer. So it means that it's close to this 1%, 1-3% that we were speaking about. So if you're looking for something quantitative, these ideas of no-local gains and Mermin inequalities can provide such a result.
So according to your rule of thumb in the beginning, that below 50% on plate, did the Honeywell H1 actually exceed all others?
So absolutely. I mean, when you look at the paper I mentioned before, where they build a table of the quantum value of all the quantum computers, the Honeywell H1 had the quantum value of 1024.
But this is also your experience.
And this is, and as you can see, it's much better than the others. So, I mean, the thumb rule perfectly matches the quantum volume, perfectly matches these results of these results. I mean. So it means, notice that this is a 6-qubit game, so there are 6 gates, and you have a 97% fidelity. So it means that the error of each gate it's much below 1%, probably in the 0.3, 0.4%. So this Honeywell quantum computer, it's quite remarkable. The only limitation, it has 11 qubits. So that's why also what limits the quantum volume. Okay, so we have 3 minutes. In the next 3 minutes, I would like to tell you about adiabatic crossover phase transition. This is taken from Wikipedia. You start in the disordered phase, you want to go order. If you go too fast, then you get stuck. You can do that also quantum mechanically. Of course, if you go slower, that's still beneficial, but it's not beneficial in an exponential way, because when you cross a phase transition, there is a closing of a gap, so the adiabatic theorem does not apply. And it means that still, so the advantage you have against law, it's going to be a power law, and this is known as the Kibble-Zurich scaling. It's a relation between the velocity that you go, oh, I see, this is v and this is eta, okay? So this is v, this is the velocity, eta, z, and d are the critical exponents. So there is a power law dependence between how fast you go and how many defects you get. The slower you go, the less defects you have. This also applies to the Floquet case, and as we had shown already a few years ago with Angelo in this EPL. Okay. So we want to realize the quantum computer, and we are going to use the transverse serializing model that has been already discussed in this talk. In this conference, it's the most natural thing to do, because transverse serializing model is a model that theoreticians like, and ZZ gates or X gates are gates that experiments are like. So there is a really perfect match. There is a phase diagram of this model. It includes paramagnetic, ferromagnetic, time crystal. Oh, Google realized the time crystal. So it's all here. It's this model. Okay, if I say new phase of matter that never existed before, except in all the papers that came before. But okay. And then you can also have the Floquet topological. Daniel discussed this, the Floquet topological region. And I'm going to discuss the simplest region, going to the ferromagnet, to the paramagnet. One word for the experts, this wiggly line it is basically QAOA. So you've heard about the QAOA. The QAOA is basically doing the same, but instead of going step by step, you go wiggling around. Okay, good. So what is our analysis? Our analysis is that we would like to study the noisy flow K-Kibble-Zurich. And here is the main message of this part. The main message is that there are two competing effects. On the one hand, the slower you go, the more Kibble-Zurich you have, the less defects you have. You get a better solution. On the other hand, the slower you go, which means you have more gates, more error. It's bad. So there is a competition between good and bad. It means that there is an optimum somewhere. Okay? And the optimum, so we do a very simple ansatz. We just assume that the number of defects is the sum of the Kibble-Zurich and the noise. But the advantage is that we can take a derivative of this function and get a relation between the noise and the optimal n. Okay? So it's very, very simple-minded, but what I'm going to show you in the remaining 30 seconds is that it works. So this is a theory calculation. Again, this is a work with Daniel and Maxime, who is here, and also Bram, and Matt, of course, from the Righetti group. So what you see here is, this is still unpublished results, but hopefully we will upload it before we upload the YouTube lecture. And so what you see here is different type of noise. So the zero noise is in blue, and you see that the slower you go, this is how slow you go. The more gates, it means you go slower. The slower you go, the less defects you have, and this is this power law. However, there is noise, and the noise at some point starts kicking in. So if you go too slow, then you will suffer because of the noise. So this is how it looks like in the advantage. The transversalizing model is fermionizable, so you can do up to very, very large systems. This is 300, many qubits. In reality, in an experiment, we can use 5 qubits. So this is even an experiment with 6 qubits, I think. And what you see here is in black the experiment. And these are two noisy models. One is a T1, T2, just the T1, T2 model, and the other is an advanced stochastic Pauli method that Maxime has introduced, in which you basically, and has been developed a lot by Righetti, in which you take the parameters from the real, you do a benchmarking of the quantum hardware, and take the values of the stochastic Pauli that you need to introduce. Well, it's not perfect. I mean, there is no perfect, the experiment is somewhere in between these two models, but the behavior, this non-monotonous behavior is universal. And actually, as we learned just 5 days ago, so we had to fix the paper, from Alessandro, you can also do it on the D wave, and you see exactly the same behavior. It first starts going down and then up. And if you see there are, we also understand the deviations at very large n. This is due to the temperature. We consider infinite temperature buff. This is a fine temperature buff, so the story is different. Okay, outlook. This is already the question. Can I ask myself a question? So where are we going now? Yes, so let me answer this question. So where are we going now is, so I think a main theme of this conference has been that there is a dichotomy between the universal model that we have of algorithms that can factorize large problems, Drake RSA, well, and nothing else, but a lot of things they can do, and the reality, these noisy superconducting circuits. And I think, as a community, the common goal is to bridge the gap. There is the knowledge gap, we need to bridge it. How can you do it? You can do it either from right to left or from left to right. So you can either improve the hardware by sitting, and even at some point maybe you get to quantum error correction, and then essentially you have killed all the noise and you go back to your idealized model. Or, and this is what I've been proposing here in this project, you actually need to improve, this is, I think, the more physicist approach, to say if my model doesn't fit the experiment, I need to improve the model. So we need to consider models that take into account the noise in a fundamental way. Thank you for listening. This is your picture, and there are more pictures on the website. Yeah.